Hello, everybody, and welcome back to my channel. Today is my 50th video, and I'm damn happy to have reached thus far. Thank you very much, my viewers, for your love and support. However, today's video is a bit different. Here, I'm again going to talk about technology like my previous one on generative adversarial networks. I'm going to introduce to you the concept of artificial neural networks or deep learning and the history behind it, the evolution of multiple technologies, and also spend time on convolutional neural networks and introduce you to recurrent neural networks. This is a series of two videos, which has four sections in this episode and followed up by another 4 or 5 sections in the following one. And it is meant for people in my MBA class or my executive MBA class who want to get into a deeper understanding of neural networks and its applications without getting into the coding aspects of it, right? And with that, let me introduce you to today's episode on artificial neural networks, right? As I said, it is two videos, a series of two videos, and this is the first video. I'm going to introduce to you the history of, introduce you to the concept of the neural network and the history of artificial neural networks. Then going to talk about the neuron, the biological neuron, and the other elements and its mirror elements in the neural networks. And the couple of neural networks that we're going to talk about is convolutional neural network and recurrent neural network. This will be followed up by 4 sessions, which I will not be talking about now. Stay put and wait for the second video. Now, with this, let's start with the history of neural networks. Way back in the 1940s, two gentlemen, Warren McClough and Walter Peetz, developed the first mathematical model of a neural network, right? This is premised on the concept of a neuron, and neuron is the basic unit of the nervous system, which constitutes three parts. One is the dendrite, the cell body, and the axon. Dendrite is the element where it receives signals from other neurons, followed by the cell body, which processes it, and axon, which connects it with further neurons to pass on a particular command. The combination of neurons transmits signals and allows us, the human body, to function through the central nervous system. With that, similarly, what McClough and Warren Peetz actually proposed was a simple model of a neuron called a threshold logical unit. This model represents a neuron as a binary switch that is either on or off depending upon whether the input signal it received was above or below a certain numerical threshold, right? This showed that connecting the threshold logical units in various configurations, it was possible to create intelligent circuitry that would perform operations like and or not, or basic computing functions. They proposed that the brain could be, through a neural network, simulated, and functions of the brain could, way back in 1940s, simulated through computing and create much more intelligent system that we could dream in that age and time. After that, in 1957, a gentleman called Frank Rosenblatt created the first artificial neuron called the perceptron, where it would take, just like a natural neuron as it take it, to take an input, as in the natural neuron, a biological neuron takes an input from the dendrite. It could take one or more input value, multiply it with a concept of a weight or a bias, which I'll talk about in a bit, and then the resulted sum would pass through what is called an activation function. Now, these are keywords, weights and biases, activation functions, which I will again explain as we go along. But for this, just remember these words. The output could be a binary 0 or a 1, depending upon whether the input values satisfy a particular threshold. The training of the perceptron involved adjusting the weights of output values to minimize the error between the predicted and actual values, and done through a supervised learning algorithm. After the 1957, there was a hiatus for a couple of decades till a major breakthrough happened in the 1980s, which was called the backpropagation technique, which was developed as a widely used algorithm to train natural neural networks, where it works iteratively and adjust what we again called, and again I'm referring the word weights, which I'm going to explain in a bit, weights of connections between neurons to minimize the difference between the predicted output and the actual output. It allows the neural networks to learn from its mistakes and adjust weights accordingly and get better over time. Coming back in the 1990s, came two gentlemen called Jan LeCun and Jeff Hilton, who actually developed the convolutional neural network and the recurrent neural network, which triggered off multiple use cases in terms of image processing, video processing, text processing, and so on and so forth, which led to a significant larger scale in terms of our understanding and application of neural networks, right? With that, let us now move on to understanding the neuron structure. A couple of minutes ago, I explained that a neuron is a basic unit of a nervous system which is used for transmitting information throughout the body. And then I did mention there is an input variable called the dendron, then there's a cell body, and there is an output there called the axon. Similarly, again, I mean, kind of going down further on this route, neurons communicate through what is called a synapse. Multiple neurons communicate through a synapse, which are junctions where the axon or the output layer of a neuron actually meets the dendrite of the other neuron and passes a signal called electrical signal that travels down the axon to the synapse, which triggers a release of chemical messages called neurotransmitters. And these neurotransmitters help us think and act in the way we do. Similar to a natural neuron, an artificial neuron has an input layer wherein it receives the signal, a hidden layer, which is a combination of multiple layers where the signals get processed, to an output layer where the outcome or the result of the inputs and the hidden layers is processed. Now let's kind of understand this with a simple example. Suppose we want to classify images of handwritten digits. It could be alphanumeric. It could be, I mean, words, say A, B, C, D, or 1, 2, 3, 4. Then what really happens that we represent each image as a pixel, as an array of pixel values, wherein each pixel is a value between 0 to 255, a range of values which allows for 8-bit encoding, which is actually a standard. And each image is represented as a configuration of 28 pixels wide and 28 pixels tall, which is a standard called MNIST dataset standard, wherein these are large enough to capture the important features of all digits and small enough to be processed in a neural network. So therefore, each pixel has a value of 28 wide and 28 tall, and so therefore about 784, which is 28 multiplied by 28, are the number of neurons that are required to give a pixelated input in the hidden layer. Now, within the hidden layer, then through what we call weights, and weights are basically parameters that determine the strength of the connection between the neurons. Like in a natural neuron, it would be the strength of the connection between multiple neurons is through the synapse. Here, it is through the weights, and which the presence of weights multiply the values and help the neurons learn faster and faster and help them to produce a realistic output. The weights are then multiplied by another set of parameters called biases, which are added to the weights, and that then gets through a process called the activation, which then triggers out an output. And we're going to talk about, as we go along, activation function in the context of multiple neural networks and the criticality of them. So simply put, just like a natural neuron has an input, which comes from a dendrite, there is a processing function, and between neurons there is a bridge called the synapse, and an output is given from an axon for the next neuron to take a particular action. Similarly, in an artificial neuron, there are input layers wherein any image or any data point or any feature is converted into pixels. These pixels have a unique value, and these neurons, all representing the unique value, talk to the hidden layer, which then calibrates it through the use of a learning algorithm called a weight or a bias, and produces an output which should mirror the input. And over periods in time, through a learning process, the output, the predicted output versus the actual output kind of become almost similar. And that's where the neural network starts predicting either a form of an input, which could be an image or a data set, to actual precision. Moving on. Like we talked about, there are input connections, weights and biases, and the activation function. Now, it's important to understand what an activation function is. The activation function is a gatekeeper that decides whether a neuron should be activated or fired, or should an action be taken or not based on the input it receives. Similarly, like the natural neuron gets activated through an electrical signal, either from a different neuron, and prompts us to take a particular action. Similarly, the activation function is actually which actually fires the artificial neurons to take a particular action. For instance, think of a neuron as a light bulb. The activation function determines whether the bulb is turned on or off. The input of the activation function is like a switch that determines the signal of a neuron, and the activation function plays the critical role in determining the output of a neural network by applying it to every neuron. And the network can learn by recognizing patterns and making decisions based on the inputs it receives, right? So with that, now let's move on to the other important aspects of the network, which is the loss function and the optimization algorithm. Here it kind of becomes a bit technical, but the loss function is basically a calculation which actually determines whether the neural network is performing a given task to a level of accuracy that it is intended to deliver. The network, the neural network is a given set of inputs and asked to make a set of predictions, like a human prediction, right? The loss function computes whether the prediction, the quality of the correct answers, and calculates the scores that reflects how far off the predictions are from the correct answers. The goal of the network is over time learn to minimize the loss function or make the prediction as close to the actual value that it is intended to deliver. Now, to be able to do that, the optimization functions minimize the loss functions by adjusting what we talked about, the weights and the biases. And the weights are actually the learning mechanisms in which the data gets massaged so that you deliver the actual output. And amongst the multiple optimization algorithms, without getting too much into it, the stochastic gradient descent works by calculating the gradient of the loss function with respects to weights and biases of the network and adjusting them to the direction that reduces the loss. So over periods of time, the optimization algorithm enables the loss, which is the error that the network is making, through a process of weights, which is the adjustment to the data to make the actual output be very close, to make the predicted output be very close to the actual output. Now, with that, let us move on to the concept of a convolutional neural network, right? Now, convolutional neural networks are used for basically, processing images of objects. It could be a word, it could be an image of a dog, cat, cow, whatever, and to predict whether another image looks like a dog or a cow or a cat, right? And it receives, suppose, very simply put, without getting too much technical into it, suppose a convolutional neural network gets receives an image of a letter A. Now, it letter A is a combination, like we discussed, of a collection of pixels, and within its hidden layers, through a process which is called convolution, identifies the unique features that make up the letter A, which is how the in between the line that makes the letter A, the two parts of it, and so on and so forth, and classifies a different image which possesses the same features as letter A. Now, therefore, the convolutional neural network has what is called the local receptor fields. Now, in the local receptor fields, it has shared weights and an activation and a pooling function, like the neural network that we mentioned a few minutes ago. Now, in the local receptor field, what the neural network does, it creates a feature map. At what feature? Suppose we are trying to identify a horse, or a human being, or a cat, or a mouse. What features distinguish a horse, right? And within that, it has, through its hidden layers, actually actually progresses in the higher level of complexity. For instance, in the first hidden layer, it will take care of all the edges. The next, the blocks. Then the others, the more complex images, and over a period of time, over multiple hidden layers, reconstruct the features which distinguish the original horse, and therefore they pool all these features together and then when it gets another image of a horse, predicts whether this is a horse or a cat or a cow or a buffalo. So essentially what we're talking about, that a convolutional neural network takes into account through its convolutional process, creates what is called a feature map, or elements of the image which are distinguishing in nature, creates a whole set of such images, pools those images to predict whether the given image represents the actual or the predicted image represents the actual image. That is the process of convolution, right? Now, in the convolutional neural network, the weights remain constant, which means it is not like the other one, the actual neural networks, where the weights change over a period of time. But in the convolutional neural network, the weights and biases remain the same over the entire feature extraction process. Simply put, set of inputs which determine whether images of a horse, cat, or a cow. It does it through a series of 6 steps called a feature, pulls the feature, and then pulls it back to say whether this image is of a cow that it has been trained, or is it of a horse or something else, right? Now, with that, let us move to the next part, which is the recurrent neural network. And a recurrent neural network predicts. Now the second thing is the recurrent neural network, which basically is a time series or sequence wherein, suppose, you are trying to predict that if somebody says, "Are you free?" what would the next letter be? Now, what essentially happens is a recurrent neural network receives a command that indicates the start of a sentence, and then it receives the word "are" and an outputs of a vector of a number that feeds back to the neuron with the help it remember what are the words which are next to "are," which are relevant here, and then says "are you," and then after receiving the phrase, the neuron assigns a probability to every word in the dictionary that would complete a statement, and if trained would actually assign the word "tomorrow" the highest probability to complete the sentence, which means you have a word "are," there's an output vector, it figures out "are," then you have the word you, which is the next output vector, then you say "free" comes the third, it actually assigns the highest weight to the dictionary, which is the logical sequence, which is "tomorrow," to complete the sentence. Now, with that, we've completed the first part of our discussion around neural networks, introduced you to I've told you about the history and the two techniques of the convolutional neural network and the recurrent neural network. Hope you found it simple. I mean, these are technical subjects, so I don't expect us to get a detailed understanding or an expert understanding about it, but hopefully you got an overview of how this technology works. Wait for the next video when I talk about the future of neural networks, the use cases and applications, and what are the limitations of neural networks. Till then, have a nice day. Goodbye. Thank you.